Part 1. The telescope that changed everything we thought we knew about the universe. The universe, as we thought we knew it, might be hiding secrets far deeper than we ever dared to imagine. For decades, astronomers worked with a well-established timeline. The Big Bang took place about 13.8 billion years ago, setting into motion everything that exists. The first stars and galaxies needed hundreds of millions of years to slowly emerge from the primordial chaos. This story felt solid, backed up by decades of observations and painstaking calculations carried out by some of the most brilliant scientists on the planet. This narrative gave humanity the comforting illusion that the grand puzzle of origins was nearly solved. However, the James Webb Space Telescope, the most advanced technological marvel ever launched into space, began sending back data that fundamentally undermined this story. The images and measurements arriving from its ultra-sensitive infrared detectors were revealing something completely unexpected. Massive, fully formed galaxies existing at epochs when they simply had no right to be there. These were cosmic structures that seemed to have appeared only a few 100 million years after the Big Bang, when, according to our most refined models, the universe should still have been wrapped in its cosmic infancy. In a single stroke, the neat timeline in our textbooks began to look provisional, fragile, and alarmingly incomplete. Imagine constructing a fully functional skyscraper, with all its electrical systems, plumbing, elevators, and luxurious finishes, in the time it would normally take you just to draw up the plans for the foundations and obtain the building permits. That is essentially what these ancient galaxies seem to have achieved. They were not tiny proto-galaxies just beginning to take shape, faint and disorganized, as we expected to find at the most remote edges of the observable universe. They were mature cosmic giants, blazing intensely with billions of stars, displaying intricate spiral structures, sharply defined galactic arms, and levels of organization that, according to our theories, should have required billions of additional years to reach. It was as if the universe had quietly built a glittering metropolis, while our theories still expected scattered villages. The problem ran deep and became disturbing for anyone who grasped the implications. Our standard cosmological model, technically known as lambda CDM, lambda cold dark matter, had been the cornerstone of modern astrophysics for decades. This model had successfully accounted for countless observed phenomena: the accelerated expansion of the universe, the cosmic microwave background radiation that permeates all of space, the large-scale distribution of galaxies forming an immense cosmic web. It had passed test after test with remarkable precision, predicting phenomena before they were even observed. But now, in the face of these James Webb discoveries, it was starting to wobble dangerously. For years, LAMB-CDM had seemed almost untouchable, a model so successful that many dared to call it the standard of truth. Some of the world's leading scientists began calling this a genuine cosmological crisis. That phrase was not melodramatic exaggeration. When your fundamental model fails to predict something as basic as when and how galaxies can form, the entire theoretical building you constructed on top of those foundations starts to crack in troubling ways. Were we merely witnessing strange statistical outliers that would eventually find an explanation within the existing framework? Or were we standing on the threshold of a scientific revolution comparable to the moment when Einstein superseded Newton, one that would force us to rewrite our most basic equations about how the universe actually works? Around seminar tables and in late-night video calls, researchers debated whether they were seeing error or opportunity. We need to think carefully about the scale of what was being discussed. The James Webb Space Telescope detected massive galaxies existing only 200 to 400 million years after the Big Bang. In cosmic terms, where billions of years are the standard units of time, That interval is practically the very next day after the universe came into existence. To put this into more everyday perspective, if we compressed the entire age of the universe into a single calendar year, these galaxies would have appeared in the very first days of January, while our models confidently predicted that such complex structures should not arise until March or even April. On the imagined cosmic calendar, these galaxies felt like fireworks exploding long before the invitation to the show was even printed. The most puzzling and troubling part was that these galaxies not only existed far too early, shattering our timing predictions, but were also extraordinarily massive and structurally complex. Some of them contained hundreds of billions of individual stars, with a total stellar mass comparable to that of our present-day Milky Way, which had enjoyed a leisurely 13 billion years to grow, accumulate matter, form stars over many generations, and settled into the majestic spiral we observe today. How could structures so elaborate, so organized, so monstrously massive have formed in such a tiny fraction of that time? The familiar processes of star formation, gravitational collapse of gas clouds, and gradual accretion of matter simply could not operate at such extreme speeds, not according to anything we thought we understood about physics. Each new mass estimate landed like a polite but firm knock on the door of our most cherished assumptions. Detailed spectroscopic data from James Webb revealed something even more intriguing and problematic. These ancient galaxies seem to possess surprisingly high chemical abundances of heavy elements. Elements more complex than primordial hydrogen and helium, things like carbon, oxygen, iron, and even heavier species, did not emerge from the Big Bang. They are forged exclusively in the blazing cores of stars through ferociously energetic nuclear fusion reactions, then scattered into the surrounding space when massive stars end their lives in cataclysmic supernova explosions. This gradual chemical enrichment of the universe should be a slow and patient process, requiring multiple successive generations of stars to be born from clouds of gas, live for millions or billions of years while fusing elements, and finally die violently, seeding space with their enriched ashes. Yet these very early galaxies already displayed clear chemical spectral signatures of several completed stellar generations, as if they had somehow compressed billions of years of normal cosmic evolution into a sliver of time. The cosmic clock, according to these observations, seemed to be running dramatically fast. Some skeptical astronomers suggested that perhaps our measurements of cosmic distance were systematically wrong in some subtle way that had not yet been uncovered. After all, measuring distances to objects billions of light years away is technically extremely challenging, and depends on multiple assumptions about fundamental physics. We rely mainly on a phenomenon called cosmological redshift, in which the light from distant objects is stretched to longer, redder wavelengths because of the continual expansion of the space between us and those objects. The greater the measured redshift, the farther away in space and the further back in time the object we are observing. But the James Webb Space Telescope uses extremely precise and sophisticated measurement techniques, meticulously calibrated against several independent standards and cross-checked using complementary methods. Systematic measurement errors large enough to erase this crisis altogether appeared highly unlikely in every analysis performed so far. Other, more imaginative researchers proposed that perhaps we were fundamentally misreading the physical nature of those distant galaxies. Maybe what looked like single massive galaxies were in fact dense groupings of many smaller objects, proto-galaxies, or compact star clusters that just happened to align along our particular line of sight, creating the optical illusion of one huge structure. Yet the extraordinarily detailed spectroscopic observations from James Webb which dissect how the light is distributed across different wavelengths, can effectively distinguish between these alternative scenarios by tracking internal velocities, chemical gradients, and characteristic emission patterns. The data consistently pointed toward truly massive, gravitationally unified galaxies rather than random line-of-sight collections of minor objects. The growing discomfort within the international scientific community was understandable. Theoretical cosmologists who had devoted entire careers, decades of intense work, to painstakingly refining the parameters of the lambda-CDM model, tuning equations, and running enormous computer simulations, now faced the very real possibility that crucial pieces of their work were missing or fundamentally flawed. This was not just a small numerical adjustment, a minor tweak to constants in the equations, the sort of routine refinement that science goes through all the time. If these James Webb observations continued to hold up under relentless, independent scrutiny by multiple teams around the world, we might need truly radical revisions to our fundamental physics, or even have to consider seriously that entirely new processes, not yet discovered or even imagined, once operated as dominant forces in the young universe. The situation became even more tangled once the broader implications came into view. If our standard cosmological model was wrong in such basic respects, what else might be wrong? Our estimates of how much dark matter fills the universe, our picture of dark energy, the mysterious agent driving the accelerated expansion of the cosmos, the very laws of gravity themselves when applied on the largest cosmic scales. Each question cracked open a fresh theoretical Pandora's box, and inside each box waited still more questions, multiplying like reflections in an endless hall of mirrors. The universe, far from being a solved puzzle, now looked like a vast cosmic riddle that had only just begun to reveal its most challenging clues. Part 2: Impossible Black Holes and the Collapse of Our Theories. Yet those prematurely formed massive galaxies were only the tip of the iceberg in the cosmological crisis shaking the foundations of modern astrophysics. The James Webb Space Telescope revealed something even more unsettling and seemingly impossible according to our established theories: supermassive black holes existing in the extremely early universe, appearing at epochs when, by every calculation and model we had, they simply could not and should not exist. Their presence contradicted timelines we once considered unassailable, turning long-trusted assumptions into open questions. These were black holes with masses equal to hundreds of millions, sometimes billions, of suns. Such gravitational behemoths are normally found in the centers of mature, giant galaxies, where they have had billions of years to grow slowly, feeding voraciously on surrounding gas, dust, and stars, gathering matter grain by grain in a process expected to be slow even on cosmic timescales. Yet James Webb detected them at a time when the universe was only a few 100 million years old, a minuscule fraction of its current age. It was as though skyscraper-sized monsters had sprung fully grown in a world where the first bricks had barely been laid. The core problem was the time required for growth. Black holes do not appear magically with enormous masses. Based on our best understanding, they begin their existence when massive stars, those at least 20 to 30 times heavier than the Sun, exhaust their nuclear fuel and collapse catastrophically under their immense gravity in violent supernova explosions. This extreme gravitational collapse creates a stellar black hole with a typical mass of 5 to 100 suns, not more. For such a relatively modest black hole to grow into a billion solar mass monster, it must accumulate an extraordinary amount of additional matter. Growth, in other words, should be painfully slow, limited by the physics that governs radiation and gravity. The accumulation process, known as accretion, is governed by strict physical limits. As matter spirals toward a black hole, it is heated to extreme temperatures by overwhelming friction and gravitational compression, glowing with radiation so intense that it pushes outward on surrounding gas. This emitted radiation forms a natural barrier. It limits how fast new matter can fall inward. This fundamental limit is called the Eddington limit, named after Arthur Eddington, who calculated it in the 1920s. The limit acts like a speed regulator on a cosmic engine. Even if a black hole feeds continuously at this maximum theoretical rate, absorbing matter as fast as physically allowed without radiation pressure blowing incoming material away, hundreds of millions, perhaps more than 1 billion years, would be required for it to grow from a small stellar seed to the supermassive scales we are observing. And that assumes perfect, uninterrupted conditions, a constant supply of gas falling directly into the black hole with no breaks, no shortages, no interference from any other astrophysical process. In the real universe, full of turbulence, collisions, and chaotic flows, such perfect conditions never persist for long. Yet here they were, these supermassive black holes, glowing clearly in James Webb's data, existing when the universe was only 400, 500, 600 million years old. The numbers did not add up in any reasonable way. It was like someone showing a towering 100-meter sequoia and claiming it was only 5 years old. Regardless of sunlight, soil, or water, biological growth has inherent speed limits that cannot be violated. In the same way, black holes have fundamental constraints on how fast they can grow. These early giants were violating every limit we thought we understood. Some scientists proposed creative theories to explain this apparent impossibility. One intriguing idea was that these supermassive black holes did not begin as small stellar remnants at all. Perhaps they formed directly as massive black holes in the very young universe through exotic processes we did not yet fully comprehend. These hypothetical direct collapse seeds could have started their lives already thousands or even hundreds of thousands of times more massive than the Sun, giving them an enormous head start the moment the universe became transparent. According to this idea, enormous primordial gas clouds, composed almost entirely of hydrogen and helium, might have collapsed straight into massive black holes without passing through the usual stage of fragmenting into stars. Normally, when a gas cloud collapses, it breaks apart into countless smaller regions that form many individual stars because of cooling and internal turbulence. But if the gas remained extremely hot, prevented from cooling and fragmenting, it could collapse as one enormous structure directly into a large black hole. The problem was that producing these special conditions required rare and very specific circumstances: pristine gas with no heavy elements that could cool it efficiently, intense ultraviolet radiation fields to keep it hot, and the suppression of any normal star formation beforehand. The scenario was possible in principle, but making it happen often enough to explain all the early supermassive black holes required assumptions that strained plausibility. Another, more speculative proposal involved primordial black holes forming in the very first instance after the Big Bang, under conditions of incomprehensible pressure and density. Quantum fluctuations in the energy distribution of the early universe could have created regions dense enough to collapse directly into microscopic black holes, which then could grow over time. These primordial black holes were purely hypothetical, never detected directly, and their existence depended on speculative early universe physics far beyond what current experiments could confirm. Yet the idea resurfaced because it offered at least one path for creating massive seeds extremely early. Some bolder researchers even suggested that black holes might grow faster than we believed, routinely exceeding the Eddington limit in ways our models failed to capture. Perhaps accretion in the early universe was fundamentally different, more efficient, more violent, less constrained, allowing sustained super-Eddington feeding. Perhaps the accretion disks around young black holes possessed exotic properties that let matter fall inward without being expelled by radiation. A few theoretical hints and limited observational clues suggested that such conditions might sometimes occur, but expanding this into a universal explanation required assuming that these exotic environments were commonplace in the early universe, not rare anomalies. What made this even more troubling was the apparent linkage between these supermassive black holes and early massive galaxies. These were not two separate mysteries. They were deeply intertwined. Modern observations established that nearly every massive galaxy hosted a supermassive black hole at its center, and that an unexpectedly tight relationship existed between the mass of the central black hole and the surrounding galaxy's stellar bulge. This correlation suggested that black holes and galaxies co-evolved, growing together through interconnected physical processes we still did not fully understand. Where one grew, so did the other. If both galaxies and their central black holes were appearing too early and too massive, it pointed toward something fundamentally wrong or incomplete in our understanding of how cosmic structures form and evolve. This was not simply a problem of black hole physics or galaxy formation. It was a deeper, systemic issue affecting multiple branches of astrophysics simultaneously. The crisis was not a crack, but a widening fissure across the theoretical landscape. Astrophysicists began running enormous computer simulations, using supercomputers to model structure formation in the early universe with unprecedented detail, incorporating every known physical ingredient: gravity, gas dynamics, star formation, supernova feedback, black hole accretion, magnetic fields, radiation transport. These simulations required thousands of hours on the most powerful machines available, and yet, even the most sophisticated and refined simulations failed to reproduce what James Webb was observing. They could not make galaxies grow that fast, nor could they produce black holes that massive in the available time, unless model parameters were stretched in artificial ways that contradicted other well-established observations. The simulations worked only when the universe was made unreal. Part 3. The Cosmological Crisis and the Alternative Theories Challenging Everything. The international scientific community found itself in an extraordinary and deeply uncomfortable moment. The stream of data arriving from the James Webb Space Telescope was not a collection of isolated anomalies that could be casually dismissed as instrumental quirks or analytical mistakes. These observations were consistent, repeatable, and confirmed by multiple independent research teams working across the world, and all of them pointed toward the same troubling conclusion: something was fundamentally wrong in our understanding of the early universe. The standard lambda-CDM cosmological model, which had reigned for decades as our most successful description of the cosmos, rested on several foundational pillars. First, it assumed that cold, dark matter, a mysterious form of matter that does not interact with light but exerts gravitational influence, constituted about 27% of the universe's total energy content. Second, it proposed that dark energy, even more mysterious, represented about 68% of the universe and was responsible for the accelerating cosmic expansion. Ordinary matter, the stuff that makes up stars, planets, gas, and human beings, amounted to a mere 5%. Finally, the model relied on Einstein's general relativity to describe how gravity shaped the universe on the largest scales. This model had achieved stunning and well-celebrated successes. It accurately predicted the existence and detailed features of the cosmic microwave background, the lingering glow of the Big Bang that filled space uniformly. It explained the rotation curves of galaxies that first hinted at the need for invisible dark matter. It described the grand-scale cosmic web of filaments and voids that defined the universe's structure. It had passed hundreds of rigorous observational tests over many decades. Lambda CDM felt as solid as bedrock. But confronted with James Webb's impossibly early, impossibly massive galaxies and black holes, Lambda CDM began showing cracks that could not be plastered over. Theoretical cosmologists attempted heroic efforts to salvage the model, tuning parameters, adding new layers of physics, exploring more elaborate scenarios within the existing framework. Some proposed that star formation efficiency in the early universe might have been far higher than what we observed in modern galaxies, allowing early galaxies to convert gas into stars at accelerated rates. Others suggested that feedback processes, supernova explosions and stellar winds that normally blow gas out of young galaxies, might have been less effective early on, leaving more gas available to form stars. Yet every such adjustment created new tensions. Increase early star formation efficiency too much, and you overproduce certain classes of galaxies, or create stellar mass distributions inconsistent with observations. Reduce feedback too aggressively, and simulated galaxies grow far too massive compared to galaxies we observe in the nearby universe. Adjusting one part of the model simply distorted another, like pushing in one bulge on a water-filled balloon, only to watch another bulge swell elsewhere. This led some of the more audacious and heterodox physicists to wonder whether the issue lay not in missing details, but in deeper assumptions. Perhaps some of the fundamental premises beneath the standard model were themselves incorrect. This was a risky position to hold, because abandoning the standard model required alternative explanations for all the prior triumphs Lambda CDM had achieved. One heavily debated alternative involved modifying gravity itself on cosmological scales. Einstein's general relativity had passed every test within our solar system, and in binary star systems, where its predictions could be checked with exquisite precision. But when extrapolated to galaxies and galaxy clusters, general relativity required invisible dark matter to make the numbers work. What if, instead of inventing new invisible matter, the gravitational equations themselves needed modification on vast scales? Theories such as MOND, modified Newtonian dynamics, and its more sophisticated relativistic extensions proposed exactly that. They suggested gravity behaved slightly differently at extremely low accelerations, conditions common in the outer regions of galaxies. These theories had achieved intriguing success explaining certain galactic phenomena without invoking dark matter, but they struggled to account for galaxy cluster dynamics and failed to reproduce the precise patterns seen in the cosmic microwave background. More recently, cosmologists explored models in which dark matter itself had different properties, perhaps warm instead of cold, or capable of self-interactions that would allow dark matter particles to collide with each other. These subtle differences could affect how quickly structures formed in the early universe, potentially accelerating the birth of the first galaxies. Another speculative track involved additional scalar fields beyond those already incorporated into cosmology. Scalar fields are quantum entities permeating space that can influence cosmic evolution. The Higgs field is a familiar example. The inflaton field, invoked to explain the universe's explosive early expansion, is another. Could undiscovered scalar fields have shaped early structure formation in ways our current models failed to capture? Some theorists ventured even further, suggesting we might need to reconsider the nature of time itself in the extremely early universe. Quantum mechanics and general relativity, the twin pillars of modern physics, resisted reconciliation under conditions of extreme density and energy, such as those that existed immediately after the Big Bang. A complete theory of quantum gravity, long sought but still elusive, might reveal that our understanding of primordial time was naive or incomplete. If time behaved differently under those conditions, our calculations of how much time early structures had to form might be systematically off. Then came the most radical possibility, that the Big Bang itself, or at least our understanding of it, required revision. The standard Big Bang model proposed that the universe began in a state of infinite density 13.8 billion years ago and had expanded ever since. But the initial singularity posed conceptual problems, with equations breaking down in physically meaningless infinities. Alternative cosmologies, cyclic universes undergoing repeating expansions and contractions, or bouncing universes where our Big Bang was actually a rebound from a prior state, could potentially create more time or different conditions for early structure formation. The debate around these alternative ideas was intense and often heated. Astrophysics, like any mature scientific field, had its established orthodoxies and entrenched hierarchies. Senior scientists who had built careers atop the standard model were naturally skeptical of proposals that challenged its foundations. Younger researchers tended to be more open to radical ideas, but faced professional risks in pursuing theories considered fringe by the broader community. Funding, telescope time, and publication opportunities all reflected perceived scientific legitimacy. Yet the history of science was full of moments when unexpected observations forced revolutions in understanding. The Michelson-Morley experiments, which failed to detect the luminiferous ether thought to fill space, eventually led to Einstein's special relativity. Galactic rotation curves that defied visible matter predictions led to the concept of dark matter. Measurements of distant supernovae revealing an accelerating expansion led to the recognition of dark energy itself. Each breakthrough met resistance, but evidence won in the end. Were we now at another turning point? Were James Webb's observations pointing toward a comparable revolution in cosmology? It was too early to know with certainty. Science moved deliberately, requiring independent confirmations, rigorous systematic checks, and exhaustive exploration of conservative explanations before accepting radical alternatives. But the discomfort was unmistakable, the tension undeniable, and a sense of approaching significance permeated the astrophysical community. Meanwhile, James Webb continued observing, gathering more data, pushing further into cosmic time, revealing more about the universe's enigmatic beginnings. Each new observation held the power to clarify or complicate the unfolding mystery. The coming years would be critical in determining whether the standard cosmological model could be preserved with careful adjustments, or whether a deeper paradigm shift awaited us, a reimagining of the very framework through which we understood the universe. Part 4. Dark Matter, the invisible ingredient that shapes the universe. To truly grasp the scale of the cosmological crisis raised by the discoveries of the James Webb Space Telescope, we need to dive deep into one of the most fundamental and mysterious ideas in modern astrophysics: dark matter. This invisible, elusive ingredient of the universe is not a minor technical detail or a footnote buried at the back of our cosmological models. It sits at the very heart of our understanding of how cosmic structures formed and evolved, from the smallest dwarf galaxies to the most massive galaxy clusters that contain thousands of individual galaxies bound together in titanic swarms. If dark matter is misunderstood, then the entire narrative we tell about how the universe assembled itself, step by step, risks being built on sand. The story of dark matter began in the 1930s, when the Swiss-American astronomer Fritz Zwicky was studying the motions of galaxies inside the Coma cluster, a gigantic assembly of more than 1,000 galaxies located about 320 million light-years from Earth. Zwicky measured the speeds at which these galaxies moved within the cluster and applied the virial theorem, a fundamental principle of mechanics that links the kinetic energy of objects in a gravitationally bound system to the system's total gravitational potential energy. Zwicky's calculations revealed something completely unexpected and deeply unsettling. The galaxies were moving far too fast for comfort, as if some hidden hand were pulling on them from the dark. Given the amount of visible, luminous matter Zwicky could see in the cluster's galaxies, all those galaxies should have flown apart long ago, drifting off into intergalactic space. The gravity from the visible matter simply was not strong enough to keep the cluster gravitationally bound at the observed high speeds. Zwicky concluded that there had to be an enormous quantity of unseen matter present in the cluster, matter he could not detect with his telescopes, but that nonetheless exerted gravity, providing the extra mass needed to explain the velocities. He estimated that this invisible matter outweighed the visible matter by roughly 400 to 1, a conclusion so radical that most astronomers of his time either rejected it outright or quietly ignored it, treating it as yet another bold but unreliable claim from an eccentric colleague. For decades, Zwicky's idea lingered on the fringes of astronomy, regarded as speculative and unnecessary. The prevailing attitude was that nature surely could be explained with the familiar forms of matter already known from laboratories on Earth. But in the 1960s and 1970s, the American astronomer Vera Rubin and her collaborators carried out systematic, detailed observations of the rotation curves of spiral galaxies that dramatically revived the concept of unseen dark matter. Rubin carefully measured the orbital speeds of gas and stars at different distances from the centers of many spiral galaxies. According to Newton's laws and the distribution of visible luminous matter that astronomers could directly map, they expected the orbital speeds to fall off significantly in the outer regions of galaxies, much as the outer planets in our solar system orbit more slowly than the inner ones. Instead, Rubin's observations showed something completely different and wholly unexpected. The rotation curves remained flat. Stars and gas in the outermost regions of galaxies were moving at roughly the same speed as material closer to the galactic center. This flat velocity pattern could only be explained if the galaxies were wrapped in huge, roughly spherical halos of invisible matter extending far beyond the bright stellar disks. This unseen matter, which does not emit, absorb, or reflect light in any detectable way, had to make up the majority of each galaxy's total mass, gravitationally dominating its structure and dynamics, and silently steering its evolution. Rubin's work, patiently accumulated night after night at the eyepiece and the spectrograph, turned what had once been a fringe speculation into a central problem in astrophysics. Since then, piece after piece of evidence has accumulated from multiple, entirely independent lines of observation, all pointing toward the real existence of this mysterious dark matter. Gravitational lensing, in which the light from distant galaxies is bent and distorted as it passes near massive foreground objects because of the curvature of space-time, predicted by Einstein's general relativity, provides a direct map of the total mass distribution, including invisible dark matter. These gravitational lensing maps consistently show that the total mass is far greater than what can be accounted for by visible luminous matter alone, dramatically confirming the dominance of dark matter in the cosmic mass budget and sketching out an invisible skeleton of mass on which the bright galaxies merely hang like lanterns. The detailed pattern of temperature fluctuations in the cosmic microwave background, the faint afterglow of the Big Bang, measured with exquisite precision by satellites such as WMAP and Planck, adds another crucial layer of information about dark matter. The specific characteristics of these fluctuations, the angular scales of the hot and cold patches scattered across the sky in the microwave background map, depend sensitively on the amount and the properties of dark matter present in the early universe. Tiny acoustic peaks and valleys in the power spectrum of these fluctuations act like a cosmic barcode, encoding how much ordinary matter, dark matter, and radiation filled the young universe. Observational data match astonishingly well with models in which about 27% of the universe's total energy content consists of cold, dark matter. Collisions between galaxy clusters provide especially dramatic and visual evidence. When two massive clusters slam into each other at speeds of millions of kilometers per hour, the individual galaxies mostly pass by one another without colliding, because galaxies are tiny compared with the distances between them. The hot intergalactic gas that fills the clusters, however, detectable through X-ray emission, interacts strongly during the collision, crashing together and slowing down dramatically because of gas pressure and electromagnetic forces. Dark matter, which interacts only through gravity and does not feel electromagnetic forces, sails straight through the collision without slowing, like ghosts drifting effortlessly through walls, or cars moving through a dense fog that cannot touch them. The most famous and thoroughly studied example is the Bullet Cluster, a spectacular cluster collision observed in remarkable detail. X-ray images clearly show two bright concentrations of hot gas at the center where the collision occurred, but gravitational lensing maps, which reveal where most of the total mass truly resides, show that the mass peaks are offset from the gas and instead sit where the galaxies passed through one another. This spatial separation between the luminous, visible matter, along with the invisible dark matter on one side, and the glowing X-ray gas on the other, provides striking, near-photographic evidence that most of the mass in clusters is indeed invisible, and behaves very differently from ordinary material. For many researchers, the Bullet Cluster became the poster child of dark matter, a single object that told a story almost impossible to explain without it. So what exactly is this mysterious dark matter? Despite decades of intense experimental searches using the most sensitive detectors ever built, buried deep underground to shield them from background cosmic radiation, we still have not directly detected a single confirmed dark matter particle. The honest answer is simple and humbling. We do not yet know. We have favored theoretical candidates, well-developed hypotheses based on extensions of the standard model of particle physics, but no decisive experimental confirmation so far. Dark matter today occupies an awkward position of being almost certainly real on astronomical scales, and yet completely elusive as a particle. For many years, the most popular theoretical candidates were a class of hypothetical particles known as WIMPs, short for weakly interacting massive particles. These particles would have masses perhaps 10 to 1,000 times that of the proton, and would interact only through gravity and the weak nuclear force, the same force responsible for certain types of radioactive decay. This weak interaction would make them extremely hard to detect directly, but it would also provide a natural mechanism for them to be produced in the right abundances in the hot early universe through a process called thermal freeze-out, which particle physicists understand in great detail. This neat interplay between cosmology and particle physics became known as the WIMP miracle, the idea that dark matter abundance almost falls out automatically if such particles exist. Multiple enormous underground experiments have searched for WIMPs for decades, attempting to detect the rare occasions when a passing dark matter particle collides with an atomic nucleus in an ultra-sensitive detector. Despite steadily increasing sensitivity and many years of data, these experiments have not found convincing signals of WIMPs, pushing the allowed parameter space for such particles into ever more constrained and uncomfortable corners. This persistent lack of direct detection has driven many physicists to explore alternative dark matter candidates and has injected a note of unease into what once looked like a nearly solved problem. Axions, extremely light hypothetical particles, originally proposed to solve a completely different problem in nuclear physics, known as the strong CP problem, have emerged as another popular class of candidates. Axions would be billions of times lighter than electrons, but they could have been produced in such enormous numbers in the early universe that, taken together, they would make up all of the dark matter. Ingenious experiments are now searching for axions by trying to convert them into detectable photons using intense magnetic fields, scanning slowly through possible axion masses, like turning the dial on an old radio in search of a faint station. But, so far, no confirmed signals have appeared. Even more exotic proposals include primordial dark matter particles formed during the very first instance after the Big Bang. Tiny microscopic black holes that could behave effectively like dark matter, or exotic space-time structures such as cosmic strings or magnetic monopoles that survived from the extremely early universe. Each of these ideas has its advocates and critics, its theoretical charms, and its serious practical challenges. Some are elegant on paper, but difficult to embed consistently into broader theories of physics. Others predict subtle signals that may simply be beyond the reach of current technology. What makes dark matter so crucial for the current discussion about James Webb's early galaxies is its absolutely central role in the formation of cosmic structure. In the standard cosmological model, dark matter acts as the invisible gravitational scaffolding on which all visible structure in the universe is built. Immediately after the Big Bang, matter was spread almost uniformly through space, with only minuscule density fluctuations of order 1 part in 100,000. Over billions of years, gravity amplified these tiny ripples until they eventually grew into the galaxies and clusters we see today, weaving them into the vast cosmic web of filaments and voids that modern surveys map across the sky. Dark matter was vital in this process for a very simple but profound reason. Unlike ordinary matter made of protons, neutrons, and electrons, dark matter does not interact with electromagnetic radiation. In the extremely hot and dense early universe, ordinary matter was tightly coupled to radiation, constantly absorbing and emitting photons. This interaction with radiation produced enormous radiation pressure that resisted gravitational collapse, effectively preventing density fluctuations in ordinary matter from growing significantly, while the universe remained hot and dense. The baryonic matter we are made of was, in a sense, held aloft by light itself, unable to sink into the growing wells of gravity. Dark matter, immune to electromagnetic interactions, was free to collapse gravitationally much earlier. Density fluctuations in the dark matter component began to grow immediately through mutual gravitational attraction, gradually forming denser and denser concentrations, deep gravitational wells in the fabric of space-time. Only after the universe expanded and cooled enough, roughly 380,000 years after the Big Bang, in an event known as recombination, did ordinary matter finally decouple from radiation and fall more freely into these pre-existing dark matter wells, like fog settling into unseen valleys and basins carved out long before. This picture, in which dark matter first builds the invisible gravitational framework and ordinary matter later flows into it to form visible stars and galaxies, has been the standard paradigm for decades. Computer simulations based on this scenario have achieved striking success in reproducing many observed features of large-scale cosmic structure. Yet here lies the crucial problem, in light of James Webb's discoveries. Even with dark matter providing this powerful head start, standard models still predict that the first substantial galaxies should not form until about 500 to 800 million years after the Big Bang, and that they should initially be relatively small, growing only gradually over time through mergers and the steady accretion of additional gas. Webb's early, massive galaxies, therefore, do not just pose a puzzle about timing. They strike at the very role dark matter was supposed to play as the universe's master architect. Part 5. Oumuamua, the interstellar visitor that defied every expectation. A surprising but potentially meaningful bridge must be drawn between the James Webb Space Telescope's cosmological revelations and an event far nearer to us, an event that unfolded in October 2017 and left astronomers across the globe scrambling for explanations. During that month, the Pan-STARRS survey in Hawaii registered an object racing through the inner solar system, and what first seemed to be a commonplace asteroid or routine comet rapidly proved to be nothing of the kind. Instead, it turned out to be the very first confirmed interstellar object ever observed cutting through our planetary neighborhood. This unusual traveler received the official classification 1I Oumuamua. The prefix 1I denotes first interstellar, and the chosen Hawaiian name, Oumuamua, can be interpreted as a messenger arriving from afar, or a scout. The title fit almost eerily well once astronomers unraveled its true behavior. When its orbital path was reconstructed backward, it became immediately evident that the object was not orbiting our Sun at all. It had originated somewhere far beyond our system, moving at about 26 kilometers per second relative to the Sun, speed far exceeding what would allow gravitational capture. It approached from the direction of Lyra, swung around the Sun in a dramatic gravitational bend, and then continued outward along a hyperbolic path that guaranteed it would exit the solar system forever. For astronomy, this moment was genuinely historic. Researchers had long speculated that debris ejected from chaotic young planetary systems must drift between the stars, though no such traveler had ever been directly seen until Oumuamua's arrival. Yet its discovery came with a frustrating limitation. It was already slipping away when first spotted. The observational window lasted mere weeks before it became too dim and too distant, even for the most sensitive telescopes. The cosmos had placed a sealed note into our hands, and then abruptly started pulling it away again before we could fully examine it. Within that short stretch of time, however, Oumuamua displayed traits that defied tidy classification. One of the earliest clues to its strangeness was its peculiar shape. Variations in brightness as it rotated indicated that it was extremely elongated, possibly 5 to 10 times longer than it was wide. This stretched form, reminiscent of a cigar, spindle, or a thin disc viewed edge-on, diverged significantly from the rounded or irregular shapes usually seen among asteroids and comets within the solar system. It had the appearance of something altered, squeezed or molded by processes outside our standard experience with cosmic debris. Another striking mystery was its lack of comet-like activity. As an object approached the Sun, any significant surface ice should vaporize, producing a coma or a dust tail. Comets, composed of icy material mixed with rocky fragments, reliably display this behavior, but Oumuamua remained visually inert. Even the Spitzer Space Telescope, sensitive to faint infrared emissions that would accompany dust release, detected nothing. It simply reflected a modest glimmer of sunlight and continued on its silent path, showing no signs of shedding gas or dust. Yet the greatest puzzle emerged when astronomers traced its outbound trajectory. Oumuamua drifted subtly off the route predicted by gravity alone, an effect confirmed by numerous independent observatories. This kind of non-gravitational acceleration is well known in comets. Gases trapped inside them sublimate under solar heat and escape directionally, nudging the comet like a steady, soft jet. But here was the contradiction at the heart of the debate. Oumuamua behaved dynamically like an active comet, but showed absolutely no measurable evidence of outgassing. No halo, no faint plume, no particulate stream. Nothing. For a field accustomed to sorting objects neatly into categories, Oumuamua presented an uncomfortable challenge. It was as though a vehicle were accelerating despite having no visible engine, no fumes, no source of power that instruments could detect. The usual labels, asteroid, comet, no longer seemed adequate. Scientists proposed various explanations to reconcile these contradictory observations. One idea suggested that Oumuamua might contain exotic ices, nitrogen or molecular hydrogen, which could sublimate invisibly, producing thrust without detectable dust or spectral signatures. Another hypothesis proposed that its surface might be coated with a dark, carbon-rich crust that trapped heat and masked internal sublimation, allowing minute gas releases through microfractures too subtle to observe, but strong enough to account for the measured acceleration. Other researchers argued that Oumuamua might not be icy at all. They suggested it could be the fragment of a shattered exoplanet, a wafer-thin slab of rock or metallic material with an unusually high ratio of surface area to mass. In such a scenario, radiation pressure from the sun could push it slightly, giving rise to its anomalous motion. This interpretation implied a delicate, sheet-like structure, more plausible for a disc-like geometry, but harder to reconcile with a needle-like shape. If true, this would hint at catastrophic planetary events in other star systems, producing debris unlike anything present in our solar system. But it was a very different and far more provocative hypothesis that captured global attention. Avi Loeb, a prominent theoretical astrophysicist and former chair of Harvard's astronomy department, argued in a series of peer-reviewed papers that the possibility of artificial origin should be considered seriously. In his view, the exact combination of characteristics, its bizarre shape, its apparent reflectivity, its lack of infrared heat emission, and its unexplained acceleration aligned more comfortably with a thin artificial object, such as a light sail, than with any known natural category. Light sails, devices propelled by starlight pressure, are not science fiction. They have been engineered and tested by humans in modern space experiments. A sufficiently thin, reflective structure could travel through interstellar space for vast periods. Loeb stressed that his proposal was speculative, but he maintained that dismissing the possibility solely because it seemed extraordinary violated scientific rigor. If Oumuamua was natural, it belonged to a class of objects previously unknown to science. If artificial, it carried implications possibly greater than any discovery of the modern era. Loeb's stance ignited fierce debates. Many astronomers insisted that natural explanations, even if unusual, were more reasonable, pointing to the lack of definitive evidence for artificiality. Others worried that sensational coverage might distort public understanding of how science functions. Despite this, some researchers appreciated Loeb's willingness to breach a long-standing taboo within mainstream astronomy, openly discussing extraterrestrial technology as a hypothesis rather than a fringe fantasy. The controversy highlighted not only scientific tensions, but also cultural ones within the field. The story broadened further when a second interstellar object entered our system in 2019. Named 2I Borisov, this visitor behaved exactly like a textbook comet, with a bright coma and chemical signatures consistent with native solar system comets. Borisov's normalcy emphasized how unusual Oumuamua truly was. Then, in 2020, a third object, later labeled 3I Atlas, was identified in archival data. It too followed an interstellar trajectory, though its properties were less clear due to late recognition. Taken together, these rare travelers hinted at a larger population of interstellar bodies drifting unseen between the stars, a cosmic traffic that our system occasionally intersects. They suggested that the solar system is not an isolated pocket, but a node within a grander galactic flow of debris, ice, rock, and perhaps, on the rarest occasions, constructs of unknown origin. And behind this cascade of discoveries lay a deeper question, one now heightened by the revelations of the James Webb Space Telescope. If small pieces of solid matter can roam freely between star systems, carrying encoded information about the environments that formed them, what might the earliest galaxies, those impossibly ancient structures Webb is now revealing, tell us about the universe that shaped them? And what might that imply about the potential for intelligence, technology, and ancient civilizations that could have seeded the cosmos long before our own species opened its eyes to the sky? Part 6. A universe bigger than we thought, and the deeper implications. As we keep unraveling the mysteries revealed by the James Webb Space Telescope and begin connecting these discoveries with phenomena like Oumuamua, we are forced to confront an even more fundamental and unsettling realization. Our understanding of the size and scale of the universe itself has been wrong in important ways. For decades, astronomers operated under a set of well-established assumptions about the dimensions of the cosmic structures surrounding us. Yet increasingly precise modern observations have shown that even our own galaxy, the Milky Way, is substantially larger and more massive than we once believed it to be. For generations, astronomy textbooks confidently stated that the Milky Way had a diameter of about 100,000 light-years, a number repeated over and over in scientific publications, educational materials, and public talks. That measurement seemed rock solid, based on decades of careful mapping of the distribution of stars in the galactic disk. Astronomers meticulously charted where the main stellar disk appeared to end, where the density of stars dropped until it became insignificant, and they treated that boundary as the effective edge of our galaxy, 100,000 light-years across. This figure turned into a fundamental astronomical fact, apparently beyond dispute and memorized by countless students as if it were carved into stone. However, more recent and detailed studies, using more sensitive telescopes, improved three-dimensional mapping techniques, and more sophisticated analyses of stellar populations, have revealed something surprising and humbling. The Milky Way is significantly larger than we thought. New measurements indicate that the true diameter of our galaxy is roughly 200,000 light-years, perhaps even more, depending on exactly how one chooses to define where a galaxy ends. In other words, we were off by a factor of 2, underestimating the size of our own home galaxy by about 100%. This is not a minor measurement error, not a small 5 or 10% correction. It is a sweeping, fundamental revision of our understanding of the closest and best studied large structure in the entire universe. How could we have been so wrong about something that seems so basic? The problem is that galaxies do not possess sharp, well-defined edges like coastlines on a map. Instead, they fade gradually, with stellar density declining progressively as you move outward from the crowded galactic center. The outer regions of galaxies contain stars that are extremely sparse, faint, and difficult to distinguish against the sky background, especially when you are trying to observe them from inside the galaxy itself. It is like trying to map the full extent of a forest while standing in the middle of it. You can see the dense trees nearby very clearly, but the scattered trees at the far, ragged edges are much harder to identify and count with confidence. The latest observations revealed that the Milky Way possesses an extended stellar halo, far larger than previously appreciated. containing scattered ancient stars, stellar streams that are the shredded remains of dwarf galaxies torn apart and absorbed by the Milky Way's gravity over billions of years, and faint stellar populations that simply could not be detected properly with older, less sensitive instruments. When you add all these outer components in properly, the true scale of our galaxy emerges as far more impressive and sprawling than we had acknowledged. The Milky Way is not a tidy disk with a neat rim. It is a vast, layered structure with ghostly outskirts stretching into the dark. This revision of the Milky Way's size carries important implications that go far beyond correcting a single number in textbooks. If we could misjudge so fundamentally the dimensions of the galaxy we can study in greatest detail, the very galaxy we live in and have scrutinized intensively for centuries, what else might we be misinterpreting about faraway galaxies that we can observe only in a much more limited, superficial way? When we look at galaxies billions of light years away with James Webb or any other telescope, we measure their total light and then infer their size, mass, and other properties based on models that we calibrate using nearby galaxies like the Milky Way. If those foundational calibrations were systematically off, then our interpretations of distant galaxies might also be systematically biased in ways we do not yet fully appreciate, infecting our cosmic census with quiet but persistent errors. This uncertainty about fundamental scales connects directly to James Webb's troubling discoveries about early massive galaxies. Part of the challenge in interpreting those observations is that we must convert the observed properties of the light we detect, brightness, color, spectra, into physical properties such as total stellar mass, star formation rate, and age. That conversion process depends critically on stellar population synthesis models that predict what a galaxy with certain properties should look like when its light reaches our telescopes. These models, in turn, are calibrated and validated using well-studied nearby galaxies. If our understanding of those local calibration galaxies contains substantial systematic errors, then the uncertainties propagate and may even grow when we apply the models to galaxies that are far more distant and much younger in cosmic time. Now let us return to the connection with interstellar objects like Oumuamua, and in particular, the mysterious 3-Eye Atlas mentioned earlier. The detection of 3-Eye Atlas was especially intriguing because it represented a potential third confirmed interstellar visitor, and its trajectory and characteristics hinted at origins possibly even more remote than Oumuamua's. The Atlas Survey System, the Asteroid Terrestrial Impact Last Alert System, designed primarily to detect potentially hazardous asteroids that might impact Earth, recorded this object passing through the inner solar system. But at first it was not recognized as anything special because the automatic analysis software classified it as a likely ordinary solar system body, just one more dot among many. Only when astronomers later revisited the archived data in detail and recalculated its orbit precisely did they realize that 3-Eye Atlas possessed clearly hyperbolic orbital characteristics, meaning it definitely came from interstellar space and was not gravitationally bound to the Sun. Its speed relative to the solar system and the angle of its incoming trajectory indicated that it had traveled through interstellar, perhaps even intergalactic, space for extraordinarily long periods of time, possibly millions of years or more, before wandering by chance into our cosmic neighborhood. In a sense, it was an ancient message written in rock and ice, carrying the memory of distant regions we may never see directly. What made 3-Eye Atlas particularly fascinating to some researchers, including Dr. Avi Loeb, who continued to investigate anomalous interstellar objects after the Oumuamua saga, were certain peculiarities in its observed behavior and spectral properties. Although the available data were limited because the object was recognized retrospectively after it had already passed its closest approach and was receding into the dark, the clues that could be extracted suggested that 3I Atlas might share some of the unusual traits that made Oumuamua so puzzling. Possibly a non-spherical, irregular shape, an apparent lack of typical cometary activity despite passing relatively close to the Sun, and perhaps hints of subtle, non-gravitational acceleration that were difficult to reconcile with a standard comet model. If multiple interstellar visitors exhibit similarly anomalous characteristics that do not fit neatly into our established categories of comets or asteroids, this would suggest the existence of a significant population of such unusual objects wandering through interstellar space. Loeb and several collaborators have argued that the observed detection rate of interstellar objects, combined with the limitations of our current survey systems, which probably detect only a tiny fraction of the objects that actually pass through, implies a surprisingly large abundance of interstellar material drifting across the galaxy. Estimating exactly how many such objects must exist to account for the detection rate requires assumptions about their typical sizes, reflectivities, and the efficiency of our survey telescopes. But even conservative calculations produce very large numbers. Space between the stars, once imagined as nearly empty, begins to look more like a vast, sparse traffic field of unseen debris and wandering visitors. This is where the potential connection to the early universe and James Webb's discoveries becomes speculatively intriguing, though it is crucial to stress that this line of thought remains highly speculative and controversial. Some researchers, again prominently including Loeb, have proposed a bold hypothesis that ties together these various, seemingly disparate threads. What if at least some of the anomalous interstellar objects we are detecting, and perhaps Oumuamua in particular, are in fact technological probes, or fragments of technology created by advanced extraterrestrial civilizations that existed much earlier in cosmic history? The reasoning behind this speculative proposal runs as follows. If the universe truly contained fully formed massive galaxies and supermassive black holes far earlier than our current models predict, as James Webb's data appear to indicate, then the conditions for the emergence of planets and potentially life could also have existed correspondingly earlier. Planet formation requires heavy elements such as carbon, oxygen, silicon, and iron, which are forged inside stars and dispersed into space by supernova explosions. If the earliest galaxies already contained multiple generations of stars, as their observed chemical abundances suggest, then the chemical enrichment needed to form rocky planets could have occurred billions of years earlier than we had assumed. In that case, worlds somewhat like Earth might have been circling alien suns when our own region of space was still dark and starless. In the previous standard cosmological picture, we assumed that terrestrial, rocky planets, capable of supporting life, could not form until the universe was several billion years old, enough time for multiple generations of stars to produce a sufficient inventory of heavy elements. That timeline implied that complex, intelligent life probably could not arise until relatively late in cosmic history, perhaps not until the universe was 8 to 10 billion years old or more. But if mature, chemically enriched galaxies already existed when the universe was only a few 100 million years old, then, in principle, planets and life could have emerged billions of years earlier than we thought, giving evolution a much longer runway on which to experiment. If advanced technological civilizations arose somewhere in the universe 10 billion years ago, or even 12 billion years ago in this revised scenario, and eventually achieved levels of technological capability far beyond anything humans possess today. They could have sent exploratory probes or artifacts across galactic or even intergalactic distances. On timescales of billions of years, even spacecraft traveling at only a small fraction of the speed of light can traverse enormous expanses. A sufficiently advanced and long-lived civilization could, in principle, seed its home galaxy, or multiple galaxies, with technological artifacts that persist for eons, coasting silently through the dark, long after their makers are gone. Of course, this hypothesis faces obvious and substantial criticisms, and it is important to state them clearly. First, there is no direct physical evidence that Oumuamua, or Three-Eye Atlas, are artificial. Neither object was observed emitting radio signals, displaying intelligently controlled motion, or exhibiting any other unambiguous signatures of technology. The anomalous features they show, while unusual, could potentially be explained by exotic natural processes that we have not yet considered fully, simply because we had never observed interstellar objects up close before the last decade. Second, applying Occam's razor, the principle that among competing hypotheses that explain the data equally well, we should generally prefer the simpler one, seems at first glance to favor natural explanations over the artificial artifact hypothesis, which requires assuming the existence of ancient, advanced extraterrestrial civilizations for which we currently have no independent evidence. Inventing aliens to explain a puzzling astronomical object sounds, understandably, like an unnecessary multiplication of entities, the very thing Occam advised us to avoid. However, advocates of the more speculative approach argue that Occam's razor does not automatically favor the natural explanation if the natural explanation requires us to invent extremely unusual physical properties or compositions that have never been observed in any other context. If you must postulate an entirely new class of comet made of exotic ices with unprecedented properties in order to explain the data, is that really simpler than entertaining the possibility of technology? Both approaches, they point out, require introducing something new and previously unseen into our picture of the universe. The question is, which addition is more coherent and better supported overall? More fundamentally, the argument is epistemological and methodological. If extraterrestrial technological civilizations really exist, or once existed, they must leave some kind of observable signatures in the universe. If we automatically dismiss every observed anomaly as necessarily natural, without seriously considering technological possibilities, then we guarantee that we will never recognize evidence of extraterrestrial technology, even if it is present in front of us. That is a cognitive bias, not proper scientific skepticism. Genuine skepticism requires examining all plausible hypotheses on their observational and theoretical merits, not excluding entire categories of explanations a priori, simply because they feel unlikely or uncomfortable. Regardless of whether one accepts or rejects the specific artificial artifact hypothesis for Oumuamua, the broader discussion highlights an important realization. James Webb's discoveries about the early universe are forcing us to reconsider not only abstract cosmological physics, but also the possibilities for life and intelligence in the cosmos. If the conditions for planets and life emerged billions of years earlier than we believed, then the temporal window for the evolution of technological civilizations is correspondingly longer. That extended window has profound implications for the equations and lines of reasoning we use in SETI studies and in our estimates of how common intelligent life might be in the universe, and it quietly suggests that the true cosmic story of mind, matter, and time may be both older and richer than anything we have yet imagined. Part 7. The Future of Cosmology and what is truly at stake. We have traveled through an extraordinary journey, passing by some of the most puzzling and potentially revolutionary discoveries in the entire history of modern astronomy. We have seen impossibly massive, impossibly early galaxies revealed by the James Webb Space Telescope. We have confronted supermassive black holes that should not exist according to our best models. We have examined the mysterious dark matter that shapes an invisible cosmic scaffold, and we have followed the enigmatic interstellar visitors like Oumuamua that refuse to fit neatly into any of our established categories. Now we need to step back and ask a deeper set of questions. What does all of this actually mean? Where is this cosmological crisis taking us? And what might we reasonably expect over the coming years as we continue to investigate these profound, layered mysteries? The first thing we must acknowledge honestly is that the astrophysical community is experiencing a level of genuine uncertainty that it has not felt in decades. This is not a small uncertainty about technical details or about some specific parameters in otherwise well-established models. It is a fundamental uncertainty about whether our basic conceptual framework for understanding the universe is adequate, or whether it requires a radical overhaul. This is not a comfortable situation for scientists who devoted entire careers to building and refining the standard lambda-CDM cosmological model. But historically, it is exactly this kind of uncomfortable moment that has led to the most important and transformative advances in science. The central question we must answer is deceptively simple to state, but extraordinarily difficult to resolve. Are James Webb's discoveries about early galaxies and early black holes merely anomalies that can be reconciled within the existing cosmological framework by applying appropriate, relatively modest modifications? Or do they constitute evidence that something is fundamentally wrong with our most basic assumptions about how the universe works? The answer to this question will determine the direction of both observational and theoretical cosmology for decades to come. Right now, different research groups around the world are pursuing diverse and often mutually competing strategies to try to relieve these observational tensions. A significant fraction of cosmologists is working intensely to rescue the standard lambda-CDM model by exploring relatively conservative modifications. These efforts focus on sharpening and refining our understanding of specific astrophysical processes that might have been more efficient or might have operated differently in the extremely early universe than our current models assume. For example, some researchers are developing models in which the efficiency with which gas is converted into stars, technically known as the star formation efficiency, was dramatically higher in the primordial universe than in nearby, present-day galaxies. In galaxies we observe in today's local universe, typically only about 1 to 3% of the available gas is turned into stars per unit of cosmic time, with the rest either being expelled by stellar winds and supernova explosions or simply remaining as gas that never collapses enough to form stars. But what if, in the early universe, under the extremely dense and hot conditions that prevailed then, that efficiency was 10%, 20%, or even higher? That would allow galaxies to build up stellar mass much more rapidly, potentially explaining the enormous stellar masses inferred at such early epochs. However, boosting the star formation efficiency arbitrarily introduces new problems and new tensions with other well-established observations. If early galaxies formed stars with extremely high efficiency, they should have burned through their gas supplies very quickly, leaving behind galaxies that are predominantly old and gas-poor when we observe them at later times. Yet many galaxies we see in the more recent universe, including our own Milky Way, contain substantial reservoirs of gas and continue forming new stars actively today. Reconciling these apparently conflicting facts requires complicated mechanisms to replenish galactic gas, such as continuous accretion of cold intergalactic gas, or frequent mergers with other gas-rich galaxies, and making the entire timing cycle work consistently across cosmic history is an extremely challenging balancing act. Another conservative approach involves rethinking the role of feedback processes that regulate galactic growth. In standard galaxy formation models, when stars form and later explode as supernovae, they inject enormous amounts of energy into the surrounding interstellar and intergalactic medium, heating the gas and driving it out of galaxies in powerful galactic winds. This supernova feedback acts as a natural brake on galactic growth, limiting how quickly galaxies can accumulate stellar mass. Additionally, supermassive black holes in galactic centers, when they are actively accreting matter and blazing as extraordinarily luminous quasars, also produce huge feedback in the form of winds and jets that can heat or expel gas from their host, galaxies. Some researchers are exploring whether these feedback processes might have been less effective in the early universe, allowing galaxies to retain more of their gas and grow more quickly. Perhaps the lower metallicity of primordial gas, which contained far fewer heavy elements than the chemically enriched gas of the later universe, changed the way gas responded to heating from supernovae and black hole feedback. Perhaps the higher average densities of the early universe compressed gas so strongly that it was harder to blow out of the deep gravitational wells of forming galaxies. These are physically plausible possibilities that are worth exploring through detailed numerical simulations. Yet, tuning feedback to solve the problem of early massive galaxies also carries the risk of creating new problems elsewhere. Feedback from supernovae and black holes plays a critical role in explaining many other observed properties of galaxies, including the tight relationship between the masses of central black holes and the properties of their host galaxies, chemical abundances, and spatial distributions of elements in the intergalactic medium, and the galaxy mass function that describes how many galaxies of different masses exist in the universe. Weakening feedback in the early universe enough to solve one problem could inadvertently break these other successful predictions of the Standard Model. Moving to more radical approaches, some theoretical cosmologists are seriously entertaining the possibility that we may need to modify or extend our understanding of fundamental physics itself. One particularly active line of research involves reconsidering the properties of dark matter. The Standard Model assumes cold dark matter, meaning particles that move non-relativistically and interact only gravitationally. But what if dark matter has self-interactions, meaning dark matter particles can occasionally collide and scatter off one another? Such interactions could change how dark matter clumps and collapses into gravitational halos, potentially accelerating or reshaping structure formation in ways that might help explain James Webb's early observations. Alternatively, dark matter may not be perfectly cold, but instead warm, meaning that the particles have somewhat higher velocities that suppress the formation of small structures while still allowing large structures to form. Or there could be multiple dark matter components with different properties, some cold and some with more complex interactions. Each of these variations introduces new physics that must be developed theoretically, checked carefully against existing observations to ensure it does not contradict what we already know, and then tested with new, targeted observations designed to distinguish among the competing scenarios. An even more direction that some theoretical physicists are exploring involves modifying the laws of gravity themselves on cosmological scales. Einstein's general relativity has passed every experimental test in the solar system, in binary pulsar systems where gravity is strong, and in the gravitational waves detected from merging black holes. But it is conceivable that when we extrapolate general relativity to the absolutely enormous distances and extremely low matter densities relevant for cosmology, subtle corrections or modifications may appear that Einstein did not anticipate and that our current experiments are not yet sensitive enough to detect directly. Modified gravity theories, such as FR gravity, scalar tensor gravity, and various extensions of general relativity, are being actively developed and tested against cosmological data. Some of these theories originated from attempts to unify gravity with quantum mechanics or from string theory frameworks, while others were motivated more phenomenologically by efforts to explain the accelerated expansion of the universe without invoking dark energy. If any of these gravitational modifications turn out to be correct, they could significantly change how we understand structure formation in the early universe, potentially allowing galaxies to form faster or more efficiently than they do in standard general relativity. However, it is crucial to emphasize that modifying gravity in a consistent way is extraordinarily difficult without creating new problems even worse than the ones you are trying to solve. General relativity is not just a single equation that can be tweaked arbitrarily. It is a mathematically elegant theory tightly constrained by principles of internal consistency, energy conservation, causality, and at least partial compatibility with quantum mechanics in the weak field limit. Most naive modifications of general relativity violate one or more of these principles or make predictions that contradict well-established observations. Developing viable modified gravity theories that pass all existing experimental tests and simultaneously resolve the new cosmological puzzles is a formidable theoretical challenge that very few attempts have successfully met. Beyond these deep theoretical questions, there is also a massive observational effort underway to gather more and better data that might clarify the situation. The James Webb Space Telescope is continuing to observe the early universe with unprecedented depth and detail. Every additional year of Webb operations brings fresh discoveries, especially as it surveys larger patches of sky and studies more individual galaxies in spectroscopic detail, revealing their chemical compositions, star formation rates, and internal kinematics. As the statistical samples of early galaxies grow, we will be able to characterize their typical properties versus their extreme outliers more reliably, to see whether there are distinct subpopulations of early galaxies with different formation histories, and to search for correlations or patterns that might point toward the physical processes responsible for their rapid assembly. Other telescopes and observatories are adding crucial pieces to the puzzle as well. The Atacama Large Millimeter Submillimeter Array, ALMA, located in the Chilean desert more than 5,000 meters above sea level, observes the universe in millimeter and submillimeter wavelengths that are particularly sensitive to cold molecular gas and dust in galaxies. ALMA can detect emission lines from molecules such as carbon monoxide that trace the reservoirs of gas available for star formation, providing information that complements James Webb's observations of stellar light. Together, Webb and ALMA are building a multidimensional portrait of what the earliest galaxies were actually like. Not only how many stars they contained, but also how much gas they held, how that gas was spatially distributed, and how rapidly it was being transformed into new stars. The next generation of giant ground-based telescopes now under construction, including the extremely large telescope in Chile with its 39-meter primary mirror, the 30-meter telescope planned for Hawaii or the Canary Islands, and the giant Magellan telescope, also in Chile, will provide even more powerful observational capabilities when they come online in the next decade. These optical and infrared behemoths will offer the spatial resolution and spectroscopic sensitivity to study individual early galaxies in remarkable detail, potentially resolving star clusters within them, mapping their internal motions, and perhaps even picking out the brightest individual stars in some of the nearer early systems. Looking further ahead, proposed space missions such as the Habitable Worlds Observatory, a next-generation space telescope specifically designed to detect and characterize potentially habitable planets around other stars, will also contribute to our understanding of when and how the conditions for life first emerged in the universe. If we eventually find Earth-like rocky planets with oxygen-rich atmospheres, a possible biosignature, orbiting very old stars that formed 10 to 12 billion years ago, this would provide direct observational evidence that habitable planets really could form much earlier in cosmic history than our previous models suggested. The connection between James Webb's cosmological discoveries and the search for extraterrestrial intelligent life is more than a playful or tangential association. It is central to how we think about our place in the cosmos and about the likelihood that we are not alone. The famous Drake equation, written in 1961 by astronomer Frank Drake as a way to estimate the number of communicative technological civilizations in our galaxy, includes a term for the rate at which suitable stars form, and another term for the fraction of those stars that host planets. If the earliest galaxies formed billions of years earlier than we believed, and already contained the enriched chemistry needed for planet formation, then there may have been billions of additional years available for life and intelligence to arise. This extra time carries deep implications. On Earth, life emerged relatively quickly on geological timescales, appearing within the first billion years after the planet formed and cooled enough to maintain stable liquid oceans. But the transition from simple microbial life to complex multicellular organisms took billions more years, and the evolution of technological intelligence took even longer. If other civilizations had a head start of several billion years over us, they could be technologically advanced far beyond anything we can currently imagine. A civilization with even 1 million years of technological advancement ahead of humanity would be effectively indistinguishable from magic, given our present capacity to understand, as the science fiction writer Arthur C. Clarke famously observed. This realization loops back to our earlier discussion of Oumuamua and anomalous interstellar objects in ways that should now feel less bizarre or hopelessly speculative, and more like legitimate possibilities worthy of careful consideration. If advanced technological civilizations really existed billions of years ago in chemically enriched early galaxies, they would have had immense stretches of time to spread across galactic or even intergalactic distances to build technological infrastructure on scales we can scarcely conceive, and to leave behind artifacts or residual technology that might persist for eons. On cosmic timescales of billions of years, even spacecraft traveling at modest speeds of just 1 or 10% of the speed of light could cross an entire galaxy many times over. Of course, all of this remains highly speculative and rests on multiple untested assumptions about the prevalence of life, the probability of intelligence evolving, the durability of technological civilizations, and their long-term motivations for exploration or communication. But the crucial point is that James Webb's discoveries have dramatically expanded the temporal window and the parameter space for life and intelligence in the universe in ways we could not have anticipated only a few years ago. That expansion justifies rethinking our strategies for the search for extraterrestrial intelligence, and being more open to potential technosignatures appearing in astronomical contexts we were not previously trained to examine through that lens. Returning to the more immediate and concrete cosmological questions, what can we realistically expect over the next 5 to 10 years in terms of resolving the current crisis? The most honest answer is that no one knows for sure. but we can outline several plausible scenarios. In the most conservative scenario, the continued accumulation of data from James Webb and other telescopes, combined with theoretical refinements of astrophysical models within the lambda CDM framework, eventually reconciles the observations with the standard model without requiring any radically new fundamental physics. We might discover, for instance, that some of the most extreme objects initially identified as very massive early galaxies are actually bright quasars, in which the light from the central black hole outshines the stellar light, biasing our stellar mass estimates upward. We might also find that improved stellar population models, incorporating more detailed physics of very massive stars in low metallicity environments, reduce the inferred stellar masses of these early galaxies. In an intermediate scenario, we may need substantial but not completely revolutionary modifications to the standard cosmological model. This could involve incorporating new dark matter physics, such as self-interactions or warm components, that affect early structure formation without contradicting other well-established observations. It could also require significant changes to how we model the formation of supermassive black holes, perhaps by including direct collapse seeding mechanisms that allow some black holes to start their existence much more massive than ordinary collapsed stars would produce. These changes would be important and would force us to update textbooks and recalibrate cosmological simulations, but they would not tear down the entire edifice of modern cosmology. In the most dramatic and revolutionary scenario, ongoing discoveries might eventually force us to recognize that something truly fundamental is wrong with our present conceptual framework. That recognition could lead to a paradigm shift comparable to the replacement of Newtonian gravity by general relativity, or of classical physics by quantum mechanics, transformative events that redefined how we understand physical reality at the very deepest level. Such scientific revolutions are rare, perhaps happening once a century in mature fields, but when they do occur, they open entirely new domains of understanding and technological possibility. What makes the present moment so thrilling and so important is that we are now genuinely in uncharted territory. For the last few decades, cosmology had settled into a kind of comfortable consensus, in which the main problems seemed largely solved, and only smaller details remained to be filled in. The standard cosmological model worked so well that some physicists began to worry that cosmology might be drifting toward becoming finished, a settled science with no major surprises left. James Webb's discoveries have dramatically shattered that complacency, reminding us that the universe remains deeply mysterious and fully capable of surprising us in fundamental ways. For young students considering careers in physics or astronomy, this is an extraordinary time to get involved. The next 10 to 20 years will likely bring major developments in our understanding of the cosmos, potentially revolutionizing fundamental physics in ways not seen since the early 20th century. The open questions are deep and real, not mere academic exercises, and the answers we uncover will have consequences far beyond professional astronomy, informing our philosophical understanding of existence, our sense of place in the universe, and perhaps even our assessment of whether we are alone in the cosmos. Ultimately, what the discoveries of the James Webb Space Telescope have given us is an extraordinary gift, a sharp reminder that we still do not fully understand the universe, that there are deep mysteries waiting to be solved, and that the quest for knowledge about the cosmos is far from complete. We live at a time when we may witness a genuine scientific revolution unfolding in real time, watching as observational data push the scientific community to reconsider fundamental assumptions and perhaps to rewrite the rules of how reality itself operates. That prospect is exhilarating, humbling, and inspiring all at once. The universe has once again shown itself to be stranger, more intricate, and more wonderful than our current theories can entirely capture. That is exactly how it should be. The moment we convince ourselves that everything is understood is the moment we stop making genuine discoveries. As long as the cosmos continues to surprise and challenge us, the scientific enterprise remains vital and alive, an intensely human expression of our insatiable curiosity about how reality truly works. The next chapters in this cosmological story will be written in the coming years and decades, and all of us, simply by being here now, have the rare privilege of witnessing that story as it unfolds. Seen from a broader cultural and historical perspective, this period may later be remembered in the same breath as the eras of Copernicus, Galileo, and Hubble, when humanity's picture of the universe expanded abruptly and irreversibly, just as the realization that Earth orbits the Sun displaced us from the apparent center of creation, and the discovery of other galaxies revealed that the Milky Way is only one island in a vast cosmic archipelago. The present crisis forces us to reconsider the narrative we tell about origins, time, and complexity. Are we living in a finely tuned, slowly evolving universe, or in a cosmos that rushes to form structure and perhaps even intelligence far earlier and more efficiently than the old textbooks suggested? For individuals outside professional science, this upheaval also carries a quiet invitation. You do not need to operate a telescope or solve tensor equations to participate in this story. Simply paying attention, following the unfolding results, talking about them, and letting them influence how you think about meaning and scale is already a form of engagement. Every major shift in cosmology has eventually filtered into philosophy, art, literature, and daily imagination. The questions raised by James Webb about beginning, evolution, and our possible neighbors among the stars are destined to do the same, reshaping how future generations answer the oldest human questions. Where did we come from? Where are we going? And who, if anyone, might be out there with us in the dark? In that sense, cosmology is not just about distant galaxies, it is also about us.